All right, welcome. Today, we're setting out on a bit of a quest. We're going to try and figure out how to build something that sounds, well, downright impossible in our digital world. The unbreakable system, a piece of software that is literally designed to never, ever fail. So, how on earth is that even possible? But let's start with a quick reality check, shall we? Because we have all been there. You are just about to post that perfect photo, you're sending a message that absolutely has to get through, or you're about to win the game, and then, boom, it freezes. The app crashes. It is so frustrating, right? With all of the incredible technology we have, why do the systems we depend on every single day still feel so brittle? Well, if we want to build a system that doesn't break, we first have to become experts in how they do break. And it turns out it almost always comes down to a simple but really powerful chain reaction. Okay, so check this out. The anatomy of a crash is fascinating. It all kicks off with something called a fault. Now, a fault can be anything. A tiny bug in the code, a hard drive that's on its last legs, maybe even someone accidentally unplugging a network cable. That fault then creates an error, basically an incorrect state inside the system, like a bad piece of data. Now, if that error isn't caught, it can snowball until you get a failure. That's the crash. That's the moment the whole thing just stops doing what it's supposed to. So the key here is that the crash you actually see, that's just the final symptom of a problem that started way, way smaller. So if these little faults are pretty much inevitable, how in the world do we stop them from turning into catastrophic system failures? And that question, that right there, brings us to the very heart of our quest. The secret isn't preventing every single fault, it's about building systems that can take a punch. And this is our goal. This is the whole idea, fault tolerance. I just love this definition from one of our sources. It calls it the art of making computing systems that keep on operating in the sight of faults. It's not magic, it's an art. It's an entire philosophy of engineering that just accepts from the very beginning that things will go wrong, and it prepares for that reality. This is our North Star for building the unbreakable system. Okay, so how do we actually do this? How do we practice this art? Well, our first principle is one you already know from real life. There is definitely strength in numbers. In the world of computers, we call this redundancy. The main technique here is something called replication. And the idea is beautifully simple. Never, ever rely on just one of anything. If you've got one super important server doing a critical job, don't just have one, have 3 or 5 or a dozen, all of them identical, all of them ready to go. These are your replicas. If one of them goes down, another one is already up and running and can take over instantly. You see, no single point of failure. But wait, how do you keep all these clones in sync? Let's walk through how this works with a really cool technique called the state machine approach. So imagine you send a request to our unbreakable app. Maybe you're posting a message. That request doesn't go to just one server. Nope. The system sends it to all of the identical replicas. Now here's the trick. This is the genius part. Every single replica has to process every request in the exact same order. This is non-negotiable. It ensures they all stay in a perfect, synchronized state. They're like digital twins. So even if one server quietly fails, the others have the exact same history, the exact same data, and they give you the right response. You, the user, never even have a clue that anything went wrong. And, this isn't just some abstract theory. You've probably used this kind of stuff a dozen times today without even realizing it. You've heard of RAID for hard drives, right? That uses multiple disks, so if one dies, your data is safe on the others. When you go to a huge website, load balancers are spreading traffic across a whole farm of servers. And clustering lets a big group of computers act like one single, super reliable machine. It's all about that same core idea, avoiding that single point of failure. Okay, so we have our replicas, we have our strength in numbers, awesome, but there's a catch. How does the system actually know that one of its parts has failed? I mean, having a backup is great, but it's totally useless if you don't know when you're supposed to switch to it. The system needs a way to talk to itself. And the solution is as clever as its name is fantastic. It's called a gossip protocol. I love this. Researchers actually trace the idea back to a time before computers were everywhere, describing it as a system of ladies and telephones. And that analogy is just perfect because that's exactly how it works. Information spreads through the network, just like gossip. Let's watch how this unfolds. It all starts super simply. You've got server A, one of our replicas. It doesn't scream its status out to the whole world. Instead, it just quietly picks one other server, totally at random, let's say server B, and just pings it a little message. Hey, just letting you know I'm up and running, I'm okay. Okay, now here's where the gossip really gets started. A second later, server B picks another random server, we'll call it server C, and sends its own health update. But, and this is key, it also passes along what it just heard. Hey, I'm doing fine, and by the way, I just heard from server A, and it's doing fine too. And this process just keeps repeating, spreading exponentially. Each server passes along everything it knows. What is just incredible about this is that this seemingly random, decentralized chatter is insanely efficient. In a shockingly short amount of time, every single server in the network gets a complete, constantly updating picture of the health of every other server. And if a server suddenly stops gossiping, well, that silence spreads just as fast, and the system knows to work around the failure. There's no central boss, no single point of failure, just whispers on the wire. So let's put it all together. We have our two big principles, replication for having backups and gossip for knowing when a backup is needed. These aren't just ideas in a research paper. They are the absolute foundation of the modern internet. Just look at how the biggest apps you use every day are built. They use something called a microservices architecture. So instead of one giant clunky program, the app is broken up into dozens of tiny independent services. So if the service that handles, say, photo uploads has a fault, it doesn't crash the messaging service. The fault is contained. And with distributed cloud architecture, these services aren't just in one building. They're replicated in data centers all over the world. So if an entire data center in Ohio goes down, the replicas in Oregon or Germany can take over without skipping a beat. This is fault tolerance on a truly global scale. Now, there isn't just one way to do all this. Think of it like a giant toolbox. This table shows just a few different models that engineers can use. For instance, LFFT focuses on using special software to handle replication at lightning-fast speeds. The FTM model is more like building with Legos. You assemble reliable applications from pre-built fault-tolerant pieces. And others, like MagicCube, are hyper-specialized for things like creating super reliable storage without needing tons of extra hardware. The big takeaway here is that there are many, many strategies, each one tailored for a specific kind of problem. So, at the end of our quest for the unbreakable system, what's the big lesson we've learned? It turns out the secret isn't actually about chasing perfection. And really, this is the most important idea of all. The art of fault tolerance is all about a shift in mindset. It's not about writing code that has zero bugs or buying hardware that will never fail because, spoiler alert, those things don't exist. It's really about humility. It's about accepting the simple fact that faults are a natural, unavoidable part of any complex system. So the goal is to design systems that are resilient, systems that can absorb a shock, gracefully find a way around a problem, and just keep on going. It's about building for endurance, not for some impossible standard of perfection. And that brings us right here to our final thought. You know, these principles we've been talking about, they're not just for social media apps anymore. Our most critical infrastructure, our power grids, our financial systems, our hospitals, even our cars, they're all becoming massive, complex software systems. And as we build that future, these ideas of fault tolerance are more vital than they have ever been. So I'll leave you with this question to think about. What's the one system, either in your own life or in our society at large, that we absolutely positively cannot afford to see fail? Thanks for joining me on this one.